All right. Welcome back to part two of explaining transverse shear in beams, and uh, um, and so now, if you believe this transverse shear formula, and hopefully you do, that it's good for all of our basic assumptions in mechanics and materials, let's take a closer look at what it means if you have a shear stress in a rectangular beam. And let's say we're given a shear that's applied here. So there's an internal shear here, V, I'll say, that's applied in this section. So if I take a cut of a beam that's loaded and I find that it has some internal shear V that's acting downwards here, um, what I want to tell you is that here the shear stress is the way that it works, and I'm going to prove this to you, is that really it's, there's these small, if I look at little increments here, right here, of the shear stress, they are acting in the same direction on the surface as the direction of the shear, and they're distributed parabolically, so that here at the location of the neutral axis, so let's say here is the neutral axis line, NA, and here I'll just draw NA right here. The shear stress is max on the surface of the beam of the cut at the neutral axis, and this right here is bam, 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 and then it gets smaller and smaller and smaller and so on and so forth, okay? Like that. And in fact, the profile here looks like, here, let's see, I'll draw it in red again. The profile here looks parabolic with max over here. So I don't know if you can see this or if this drawing has gotten too sloppy here, but that's what the intensity, this is what the intensity looks like here. These are my max shear stress, and this is a parabolic stress. So the shear stress profile is parabolic. And if I drew this in 2D, this is how I would draw it. I would just draw it like this. Here I would have this. Here's my surface right here. I have all my little shear stresses with the arrow being max at the neutral axis like this. And here is my neutral axis, and A right here. And the intensity of this is parabolic. Okay? And here is tau max at neutral axis location. All right. So I'm gonna show this to you. So here, if I'm given a rectangular cross section, so let's draw a rectangular cross section here, like this. Okay. And I know that my neutral axis is here at the center. This has a height, which I will say each of these is h over 2. H over 2. It has a width, which I will call b here. Has a width b. There's my cross section. I'm given an internal shear V, and cross section dimensions here, and I want to be able to calculate the transverse shear, find the transverse shear stress at any location above the neutral axis. Okay, at any y above the neutral axis. And hopefully this will show that the distribution of this is parabolic. All right. And so here, let's see, my y location at any y location. So I would have here, let me draw this as y, bam, like this. Let me call that y1. Okay, so that our notation. So this is my plus y direction is upwards, and I'll say the location I want is at any location y1, which will be here. This will represent y1. Okay, so if I want to find the transverse shear here, I just need to straight up apply my transverse shear formula. And that transverse shear formula is tau is VQ over IT, okay, or IB, which is the width. Here, I'm going to say T here, and T represents the width at the location you want the shear stress, the tau value here. Right, and so here in this case, let's see, for this is pretty simple. V is given, so check. Let me use a different color. V is given, check. T is just equal to B. Okay, so that's easy. And then I, you can cancel, is the moment of inertia. I is the moment of inertia of the entire cross section of entire cross section. Okay, so you don't want to have to just take the area above the cut. So here, let's see, let's calculate these properties. So first and foremost, t is equal to b, and here I, so there's t, I is just 1/12 base times height cubed. All right, so that's easy for a rectangular shape. Now, the last part of this, so now we have I done, okay, is Q, the first moment of area. Q is first moment of area about the neutral axis, okay? And the way you calculate Q, and you might see it in some textbooks as Q is the sum of A prime times Y bar prime. You'll see it as that. And what it means, or really what it should be for us here, is A1 times Y bar 1, okay? And what this means is that A1 is, the way you want to treat this is A1 is the area, all area above where you want to know what the shear stress, the transverse shear, want tau, where you want the tau, and Y bar 1 is the centroid. It's the geometric centroid of A1 measured from the neutral axis, okay? From the neutral axis. And this area could actually be all the area above, or, I want to put in orange here, be all colorful, or all the area below, okay? Or below where you want to know the tau, okay? Where you want the tau. Okay, so in this case here, this dimension here is h over 2 minus y1. Yes, okay, right there. And this is still b. And this area right here, all the area above where I want the shear stress, this is my A1. And so in this case, in this particular case, Q is equal to B, the width, the area of this blue zone, times H2 minus Y1. There's my area, times the centroid. And I'll do the centroid in purple. The centroid of A1. Okay, here's my centroid, and this distance from the centroid to the centroid of A1 from the neutral axis. So this would be Y1 bar right there. Okay, Y1 bar. And in this case, it's pretty simple. It is just, it's Y1. This arm is Y bar 1. Let's put it over here. Y bar 1 is Y1 plus half this distance right here. Half this distance right here, right? This distance right here, which is 1/2 h over 2 minus y1. Hey, and so here I would include y1 plus 1/2 times h over 2 minus y1. And let me put this in a rectangular bracket or square bracket right there. Bam, and don't let that mess you up. Okay, so this is y1 bar is equal to that. It's defined as that right there. And so here, this is my Q. Now I just put it all into the transverse shear formula. So combine into tau. Okay, and so I would get tau is equal to VQ over IT, which is V, some value V that I don't know, times 1/12 base times height cubed over here, times the width at the location I'm interested in, which is B also, okay, times this whole mess right here, which is B times H over 2 minus Y1, Y1 plus 1/2 H over 2 minus Y1, bam. So if I do some algebra, or just some algebra and make this into a little bit cleaner, what this will eventually become is 12V over BH cubed times h squared over 8 minus y1 squared over 2. And then if I factor out a half over there, then I get that this tau is equal to 6v over bh cubed times h squared over 4 minus y1 squared. And here, this term right here should scream to you parabolic. Parabolic. And here, right here, so as y1 varies, going up and down, right? It should be parabolic, right? It's going to change because of the y1 squared right here. And you can see that at the very end, at the end of the beam, when let's put this in green, when y1 equals h over 2, so this is either the top or the bottom, this term becomes 0, so tau equals 0. And then when y1 equals 0, we're going to get tau max. Okay, tau max occurs. Okay, and you can also prove this by taking the derivative, d tau over dy1, and then setting it equal to 0 and solving for y1. You'll end up with y1 equals 0. Okay, so here, these are the things, and this is just proof that this parabolic distribution that we had over here is good. Okay, and the max always occurs at the neutral axis, and that's one thing you can always kind of at least as long as you have linear elastic behavior and everything, the max occurs at the neutral axis and the edges have 0 shear stress. All right, so hopefully that was helpful. And we'll stop our shear stress explanation here, or our introduction to it, and hopefully do some more example problems later on. All right, let me know if you have any questions. Bye-bye.